Good morning, everybody. Welcome to Innovation 2. My name's Dave, and I will be here to introduce speakers and try and keep everybody on time. So first up, we have Kevin Meinl from Scion, and he will be talking about secure path-aware internet routing.
Okay, thank you, Dave. I'm just wondering where the clicker is. There it is. I think that's the one. Okay, so I'm here to talk about Scion. This is something that some of you may not have heard about at all. Some of you may have heard about, and others may have had, certain misconceptions about Scion. So I'm kind of here to really explain what it is and what it does and how it can be useful on the internet. So Scion started as a research project at the ETH in Zurich, which is the Federal Technical Institute. It was probably even about 10 years ago, but since then it's sort of expanded into a commercial implementation and is also used on some production networks as well. But just to sort of give a background of what it's useful for. So I'm showing this kind of famous, or maybe it's an infamous, attempted mapping of the internet from CADA in the US, and it really trying to sort of show you all of the sort of interconnected networks that form the internet. And really, it's pretty much a kind of spaghetti spider's web. You can't really sort of discern a lot of detail from this. But what I'm showing that for is really to sort of show you that, how many sort of different possible paths there are across the internet. We've heard a lot that, this week, how many autonomous systems there are, so over 75,000. And then there's, getting on for nearly 1 million advertised routes on the global internet. So, just adding up all of those, possibilities, that is a lot of possible paths. And as I'm sure many of you are aware, BGP, is the interdomain routing protocol, but this is really based on unverified trust between networks. So there is no built-in validation that the route advertisements are legitimate, and any network can announce any ASN or IP prefix. So in a sense, the networks can masquerade as other networks, and another issue is that the sending and receiving networks can't always decide the path that the intermediate routers on the network are sending their traffic across the internet. So that's a kind of inherent issue. So why is this a problem? So again, we already heard this week about route leaks and route hijacks. You probably have some familiarity with those. A route leak is really perhaps more of an accidental misdirection of traffic through an unintended path. That can result in delayed traffic or undelivered traffic. It can be used for more malicious reasons. And then we also have route hijacking, so that is an intentional false announcement of a route, and that will send traffic to the wrong destination and is used for denial of service attacks and traffic interception and so on. There's been a number of infamous attacks, but this is going on every single day to some extent. But then perhaps less under consideration recently, until quite recently, is the data sovereignty breaches. So BGP routing can send traffic across geopolitical boundaries, and this potentially is breaching national and also supranational legislation. So for example, you have GDPR, which is an EU legislation pertaining to where data can be sent. And one example of that is back last year, some Australian healthcare data was transferred through a third country when it should have been sent to Sydney, I believe. So this is becoming a growing issue. And that's sort of an illustration here of the potential paths that Data can be sent across a network, and if you want your traffic to stay in Germany, this is just one example, but potentially it could be routed through the Netherlands or Belgium or Switzerland, for example. So I think this slide shouldn't be in here, but there's a number of reasons why routing security has been overlooked, which have sort of been well explained and examined, and there have been different measures taken, such as Manus, to try to address this. But there's sort of been three main methods so far. The one that's been pushed really for the last several years is RPKI. So this is providing cryptographic assertions of IP prefix ownership, in other words, which ASNs are allowed to originate that. That allows routers to validate the ROAs and generate route filters. But the issue with this is that it does require widespread deployment to be effective, and at the moment, less than 50% of prefixes globally are signed as of today. But even if you have created ROAs for your resources, you need to do something useful with that, and that really requires doing route origin validation. And at the moment, they're sort of estimated that only about 5% of networks are actively doing that. And even if you are doing that, this is only doing origin validation and not validating paths across the internet. So there was another attempt to sort of address this with BGP-SEC, which is building on the RPKI to provide the cryptographic assertions for each router hop on the route to the destination. And in principle, this prevents unauthorized insertion of ASNs into the path, which can be used to circumvent RPKI. But the issue with this is that it needs to be explicitly supported by all the routers on the path to achieve the full benefits. One of the arguments was it was quite computationally intensive and introduces significant delays in route convergence. Even then, there's explicit path selection isn't possible. But the main issue really with BGP-SEC is that there's almost no deployment as of today. So ASPA was devised really as perhaps you'd say a developmental stopgap technology. This allows ASNs to authorize other ASNs to carry their traffic on the internet, and it works out of band, so it's not it hasn't got a reliance on having all the routers running it. But again, it doesn't provide the assurances that traffic will follow particular validated paths. So this is bringing us to Scion, which is a solution to really to provide secure path awareness, but also you undertake path selection as well. So in sort of summary, it's an inter-domain path-aware architecture. It has a number of benefits, one being fast path failover. It's possible to switch to backup paths very quickly. But the real advantage is with path control, so source endpoints can select AS paths and choose their paths across the internet. So this provides higher assurance that the packets will follow certain paths. It provides assurances against hijacking prevention, and it also allows for geofencing as well. And it's based around something called isolation domains, so trusted groupings of ASs. Probably isolation domain is not the best terminology. It's just something that was introduced some years ago, and it's just too difficult to change now. Perhaps trusted domain would be a better word for this. But these ISDs are logical groupings of ASs that share a uniform trust environment. And they're ministered by a group of ASs that form what they call a voting mechanism. They're known as the core ASs, or the ISD core. And what they do, they create their own trust root called the trust root configuration, which is essentially a collection of X509 certificates with added ISD information. And this is negotiated by the core ASs in each isolation domain. and they're able to issue certificates for each AS in that domain. So it's not reliant on third-party trust. And this is really what's used to provide the building blocks for Scion. So there are sort of three main components to this. You have the control plane, which is really there to discover the valid interdomain paths and then construct and disseminate these path segments. It has a sort of routing identifier based on what they call an ISD-AS tuple. And then, but the intra-AS communication just relies on the standard interior gateway protocols that you would normally run. There is a control plane CPI, which is validating the trust route, and that's used by the control plane. But then the data plane itself will combine the identified path segments into end-to-end paths, and it will forward traffic using those paths. So the deployment model is that Scion routers are set up on the borders of each AS. So these are sort of specific Scion equipment. Ideally, this will be supported in sort of standard vendor implementations. At the moment, there's equipment available from Anapaya. You can also build your own routers as well with the open source implementation. But these are essentially peer with other Scion-enabled networks, and will collect the customer traffic. And then it's actually the control services which can be part of the router, but they can also run in Docker containers. They'll discover and map the network's paths. So there isn't any change needed to the internal network infrastructure. You can put Scion stacks on the endpoints, which provide some of the control services or the control for this. But there's also legacy endpoints that can be used for non-Scion enabled networks. So the idea behind grouping ASs into these isolation domains is that it isolates the different control planes and reduces the communications overhead. And then at the AS level, it establishes paths on an AS basis rather than on a prefix basis. So the idea is to reduce the amount of sort of global communication. And the way it does this is using something called beaconing. So these beaconing messages are used to advertise and construct the path segments. There's a beaconing algorithm that's used between all of the core ASs, and there's also an intra-AS beaconing algorithm as well. So it's possible to communicate between between different isolation domains. The endpoints, as I mentioned, they look up the path segments and combine those to form the end-to-end paths. So the control services, there are essentially 3 of these. There's a beacon server, which is the sort of essentially the advertisements of the segments. The path server is the service that maps these ASs to paths after the beaconing process or during the beaconing process. And then you've also got the certificate server that's you're managing the trust, the certificate trust there. In practice, these are all running on the same, like in the same virtual machine or on the same box, but they are separate processes. And then you've got the border routers that I've already mentioned. Again, in principle, these can be sort of simpler than your average internet router. So they're using a lot of these are using standard PCs. So perhaps one of the the benefits here are that BGP will generally select routes based on a inverted commas lowest cost, regardless of whether these are the most whether these in practice are the most optimal, or whether these paths are meeting particular requirements. Because the way that the beaconing works and the way that the path segments are stored and constructed, it doesn't rely on iterative convergence or forwarding table updates. So it does allow this sort of faster path exploration, which and so in principle that you can switch paths, or you actually use multiple paths across the network very quickly. You can make that selection very fast. But the important thing is that the applications can actually, particularly SCIAN-aware applications, can choose paths, based on optimal characteristics. At the moment, that's often sort of, geographical information, but you can also put in other parameters into that system as well. But the other important thing is you can use multiple paths simultaneously as well. So there are some other benefits this is already implemented, so there is the path authorization, so the hop-by-hop authorization. There are some extensions underway, so there'll be proof of forwarding, so cryptographic proof of forwarding. This is something called EPIC. It's not in the commercial implementation at the moment, but this is being worked on. And then actually there's also an intra-domain extension sort of based on a similar technology called Fabrid or Fabrid. Again, that's maybe at the moment sort of research experimental implementation. Okay, so that's the theory, that's the background. So is this actually being used? And the answer is yes. This is currently being used by this Secure Swiss Finance Network. So this is a network of Swiss financial institutes, including the Swiss National Bank, operated by an operator called SIX, the Swiss Financial Infrastructure Operator. And one of the reasons for this is that they really wanted to have an enforceable governance concept. They wanted to have geofencing, but they wanted this to be supported across multiple ISPs as well. That was the sort of idea behind it. So, this is supporting around 300 finance institutes and handling quite a lot of financial information. But the reason, the question is, why was SCIAN adopted? One reason was that the existing finance IP network was actually reaching its end of life. But that network actually didn't limit connections to the rest of the internet. So there wasn't a great deal of protection against cyber risks, and there was a sort of the geofencing issue as well. A lot of it was based on point-to-point connections that had actually had a lot of single points of failure. They were simply leased lines, single with just no backup route. But as I said, the sort of lack of strong governance was also a very key thing here. So this has been rolled out. This is actively used. And okay, one of the questions was, what are the lessons from this? How well is this working? And I think it's working pretty well. There's been some sort of teething issues. Perhaps the harder than expected challenge was actually setting up the isolation domains and the creation of the whole sort of governance and admission criteria. This perhaps is not a technological problem. It's more a sort of human or administrative or governance issue. But this turned out to be a little bit more complicated than perhaps was anticipated. And particularly, there was a lot more manual checking and a lot more sort of manual interaction than perhaps you would have hoped. As with all sort of new crypto stuff, there was sort of some interesting challenges with the PKI stuff. And then it was realized actually that certificate revocation hadn't really been included in this, but these certificates will expire within 72 hours. They're renewed every 72 hours. So, in the end, this will time out quite quickly. Generally, the SCIAN projects are quite new, so not all the features are implemented. I hinted at that with the EPIC extension and the Fabrid stuff. And actually, another major limitation is that the inter-AS path control is quite limited. So it's sort of an either-or thing at the moment. You can't sort of do fine-grained policy control, but that's something that is coming. But yeah, generally, people are sort of getting to learn this and getting to grips with this. But the good thing is that the practical experience with the path failover and failback has been occurring within a few seconds. So that is working as intended. So it's not just a Swiss financial network. You've also got the Swiss healthcare network has adopted this and is using this to interconnect some hospitals and doctors' surgeries. There is an active education network connecting with, using Géant as the sort of backbone, but it does have connections out to Korea and National University of Singapore as well, I believe. So I think there's also a connection to the US too. So it has sort of global reach, and there is sort of this is actively being used. And then currently looking at the Swiss Association of Swiss Electric Companies, so power utilities are actually considering using this in their backbone as well. Okay, so how to use this? There is a commercial implementation company called Anapaya, which is again a spin-off from ETHZ, but is a company, commercial company in its own right. There is an open source implementation that's a development of the work that came out of ETHZ, and also a lot of the work that was done by Anapaya. So they released a lot of the source code into the open source. So I think that's sort of good news, especially after the open source BOF we had yesterday. And there are some other implementations, very experimental at the moment, but for P4 and Rust. We're going through the standardization process with the IETF, so this is really important for a lot of, particularly government bodies and things that have, regulatory issues. So actually there's been, SCION has been sort of presented and has been discussed at the IETF. There's currently 5 drafts being discussed through the PANRG PANRG research group. So I think the pedants will point out that is the IRTF, not the IETF, but they have their meetings at the IETF. But the plan there is actually so this is documenting the different elements of SCION, like the data plane, the control plane, the PKI, and the different components. And the plan is to submit this as an RFC through the independent submission stream. So that is work that's been underway for over a year now. And then there is the SCION Association to support all of this. This was created just over a year ago. It's got sort of 3 main goals. One is to act as the governance structure for the SCION open source implementation. You provide support to that, ensure that there are options to the commercial implementations. It's also there to support the standardization process. So mostly at the moment that's through the IETF, but then also to raise awareness of the SCION technology, and also try to find users, people who are interested in using this, and who can help support this as well. So there are, I think, 13 members at the moment, mostly Swiss organizations, but the plan is obviously to grow this to an international base as well, which is one of the reasons why I'm here speaking, and really just to get that sort of, ensure there's sort of multi-stakeholder support for this technology. But there are quite a lot of users out there using this in different parts of the world. This is just an example of some of the users and researchers, people involved in SCION. So it is it's a growing usage and growing support for this. So that's pretty much the conclusion. I would like to point out, if you're interested in learning more about SCION, there's actually quite a lot of references. Some of the documentation is very good. I was actually very impressed when I joined SCION and read some of this. So really is quite a lot of comprehensive information, and if you're really, really keen, you can take the book. It's about this thick. It's actually a physical book, and quite a heavy read, but it's a pretty comprehensive read. So just to point out that is available. And if you're interested in taking a closer look at the code, you can also download that from GitHub. It's available there. So I think that's pretty much brings me to the end.
Thank you, Kevin. Any questions for Kevin? Form an orderly queue. State your name and affiliation. Yes, like to.
Martin Winter from NetDev, working on FR routing. So first of all, I would be very interested on the FR routing community, especially NetDev. We're looking at if it's interesting to make another implementation of Xyon. So if anyone of here is interested, I would highly appreciate if you would contact me and talk about it. But then I have a question that was mainly on the slide where you compared Xyon to BGPsec and APKI. I mean, instead of having another protocol, wouldn't it be easier to use APK pass validation? I mean, you don't need to have it completely deployed, the same like as Xyon. You need to deploy it between the network who need it, and if you need it inside the AES, another thing, you could potentially use segment routing inside. And I think that sounds to be much easier and no new implementation of protocol needed.
So, I mean, I think that this is, Xyon is not just about path awareness. I mean, I think this is its strong selling point. And of course it was, Xyon came about probably sort of in parallel to these other possible solutions. But I think, Xyon at the moment is, providing this solution today, whereas some of these other things are, are maybe research or experimental. And, there was a need in particular communities to have an implementation that would support what they needed today. And I think that's sort of one of the primary reasons as to where this goes in the future. I mean, I think that this is also a discussion we're having through the IETF and with, in these sorts of communities to see where this will go. But I think it was a sort of something needed to be done here and now, and I think that's the reason for this or why this was done.
Shengin?
I have a question. I think this work is interesting. I just wanted to know if NIS can belong to Federation.
It can, yes. This is the straight answer. So I'm not sure if this is done today. So it can be done today. Whether anybody is doing it, I don't know. But yeah, in principle, it can be done, yes. You can belong to more than one ISD. Each one AS can belong to more than one ISD.
Thank you.
Robin?
Robin from Huawei. My basic question is that for the Xyon architecture, what's the data plane? You still use the IP address as the identification in the data plane?
It's ISD and the AS number. It forms a tuple, so that's the identifier for that.
Okay, that means a new identification.
Yes.
Okay,
Yeah.
I understand. Okay.
And Dhruv.
This is Dhruv. Just, I think I might have misunderstood. What he's asking is, at the data plane, the packets are still IP, right? IPv4, IPv6.
They are, yes, yeah,
So
correct.
that
yeah.
was, I think.
Oh, sorry, yeah, okay, sorry.
No, that's if this is the still IP packet, I mean that you still use the IP forwarding in the data plane for the sign.
Sorry, could you repeat?
I mean your IP address because you have the source address, destination address in the packet, or you use other identification in the.
So the forward is done on the base. So it uses uses IPv4 on the underlying transmission mechanism, but the path forwarding is done through this ISD AS tuple identifier.
Okay.
Are those carried in the packet?
So yeah, they're on. I think they're added to the packet. Yeah, they're part of the packet.
I
yeah.
must have misunderstood. I was thinking of something else. Anyway, my one question, this is Dhruv, was most of the deployment that we have so far talked about is power, finance, healthcare, very private networks. What's the thing about, like, if you want to introduce this in the crowd here, which is running sort of more ISPs, public networks, how would that work? And what would be the transition? Because that's one thing that we have always seen with new technologies, something that we have not focused, thinking about V4, V6. For instance, how would one transition into this if they want to already running BGP, for instance?
Yeah, I think that's a really excellent question. So, this was devised, I think, primarily for users or networks that have, very specific data governance or, specific sort of, how we say, transmission requirements. But it has been designed with, multi-domain or multi-use use in mind, because you have the inter-ISD capabilities as well, and that will be defined on a sort of ISD by ISD basis. You'll be able to define each ISD will be able to define who they want to exchange traffic with. It's not to say they can't exchange traffic with the rest of the internet. It's not saying you're completely cut off, but you can define that. What is that you're sending between each ISD? That is to sort of create islands of trust for specific use purposes. But if you look at the Sierra, which is the education network, the Cyan Education Network, that's doing probably the sort of pioneer of the sort of inter-ISD, different use case. Transmission, let's say. So I think that in the education field that will that there's more applicability, and I think also there's that sort of working on that sort of how does this work between non-private networks.
Thank you, Kevin. All right.
Okay.
Next speaker is Chang Ying, and she will be talking about my new favorite thing, BGP Watch.
Hello, everyone. My name is Changjing An. I'm from Tsinghua University. And my topic is developing a collaborative BGP routing, analyzing, and diagnosing platform. And the motivation of the platform is to provide useful tools for operators to monitor their network. First, I will give some background information, and then I haven't changed, but why it turn? I think it's this. I should this way. Back this way. Okay, thank you. And then I will introduce the hijacking detection algorithm and the functions of the platform. And finally, I will discuss some future work. This work was carried out by 19 organizations and funded by IPNIC Foundation. Most of the organizations are in regions from Asia Pacific regions. At this conference, we talk a lot about BGP security and BGP hijacking. And we all know that BGP hijacking often leads to catastrophic consequences. Here are the classic scenarios of prefix hijacking and path hijacking. I won't dive in the detail of them. I think all of you know well of this. So we have discussed several solutions to BGP hijacking and BGP security, and as Kevin has presented the Cyan protocol, and also other solutions such as RPKI and SPA. All this has been discussed a lot at the conference here, but there isn't a one-size-fits-all solutions. So that's where we are here and do some discussion. Now here, I mainly focus on how to detect BGP prefix hijacking based on the routing information from multiple vantage points. And after the hijacking events was detected, some mitigating solutions are adopted, such as announcing a more specific prefix or contact other networks to filter the routes. When a prefix hijacking events occur, as usually there a prefix was announced by multiple AS, so which is referred to as MOS. So MOS is a critical characteristics of source hijacking. But unfortunately, MOS isn't only caused by hijacking. There are many other issues that will also cause MOS, such as multi-homing, traffic engineering, DDoS mitigating, and any cache addresses. All this will also cause MOS. So determining the legitimacy of MOS is a major challenge now. To solve this problem, we proposed a rules and machine learning combined method. And initially, initially, the machine learning classifier was trained using the knowledge from ROA, RS relationships, and ground truth data. And after extract these features are trained, and so we get the machine learning classifier. And during the operation, the platform will fetch BGP route feeds and get the MOS. And then, first, this rule-based filter will filter this MOS and get the potential hijacking events, and then these potential events will come to the machine learning classifier, and finally we get the potential source hijacking events. For rule-based filtering, these are the filters. First, we have a ROA filter, which will compare the prefix announcement with ROA entries, and to check if they are valid. And this filter will sync with public repository using RoutineNet every minute. And the RR filter will use internet routing registries to assist in filtering, and it syncs every day. And also we have provided customer filter, topology filter, admin filters, and frequency during filters. All these filters are used to aid the MOS filtering. For the machine learning-based filtering, the features we used include MOS type, S-rank difference, business relationship, geographical relationship, and the announcement activity of the AS and the hijacking activity. And also the S-name, edit distance of S-name, organization, and description of this information are used to train the classifier. And so we get the machine learning classifier, and experiment shows that it can reach high precision and recall and accuracy. For path hijacking detections, so state-of-the-art detection technique include treat all unseen links appearing in the control plane as suspicious event, and then validate the event through that data plane probing. But there are some limitations because that not all unseen links are because of hijacking. And there are such as backup links and policy changing. All this will cause unseen links. And to detect all these unseen links in data plane will cause intense data plane workload, and so makes the platform inefficient and difficult to guarantee real time. So the solutions of the platform is to evaluate the authenticity of unseen links with link prediction and filter the benign unseen links. So the link prediction is a technique for inferring whether a link is likely to exist between two nodes from an existing observable portion of the network. So here comes the question, is S-link predictable? Fortunately, the graph characteristics of S-level topology makes it is predictable. There are the power law distribution and navigate degree correlation and hierarchical structure. All these characteristics makes it is possible for S-link prediction. Here is the architecture of the link prediction classifier. Here, we want to predict if the link between A and B, if there exists a real link between them. First, we get the subgraph of the topology, get this subgraph, and then we embedded the subgraph into a matrix and get the node latency features. And also, we get node-related information such as relationship, as location, as type, and rank. All this information are extracted, and we get node explicit features. And all these features we combine, trained with positive and negative samples. The positive samples are the real existed links, and the negative samples are not existed links. We sampled randomly, and then finally we get after training, we get the predictor. And the accuracy experiment shows the accuracy is high. Here is the framework of the hijacking detection system. Here, we get the phase between phase, and then we get the S-links, and then check if it's reliable S-link or unseen S-link. And then check if the link is with an unseen S. And if yes, we use some rules to fit the links. And then we push that the remain links to the link predictor, and then we get a prediction value, and to check, then we'll check if it's larger than the threshold. If yes, we think it's a valid link. If no, we push them to a new rules, and then use the rules to evaluate the suspicion, and then finally we get the link path hijacking events. These are the rules we used to detect to further evaluate the links. The first is the S-path length. If S-path hijacking, usually the hijacker will append the S to the end of the path, so makes it is longer than regular S-path. And the second and the third is to check the last the single digital SN if there exists, and the edit distance, because these links usually are caused by operators mistyping. And also we'll check the S-path loop. This usually is caused by BGP poisoning. And also we'll check if the airpath violates the value-free rule and if it causes traffic detour. Each match of these rules will increase the suspicion score. And finally, if a path score reaches a threshold, it is judged as hijacking. Because there are a huge amount of routing data from all these sources, so we adopted parallel computing and clusters to handle big routing data. Firstly, the data was gated, and then we use producers to send this data to the Kafka, and then the consumer gets the data from Kafka, and then finally get the result. Also, the platform will evaluate the harm level of each event by judging how many domain names in the prefix, and if the S is an important S hosting many hosts. We get the domain information from the top 1 million domain Tranquil and Cloudflare, and convert those domains to IP prefix. And also we get S-type from SDB, which is a research data set that maps SN to organizations and industry types. And now the platform is open sourced, and you can, if you are interested, you can check the code at all these URL. Next, I'll move to the platform functions. Left is the homepage of the platform. You can see some statistical information, and right is a real-time monitoring page. You can get all the hijacking events information from S and the country and the prefix, and you can search packet level and S number, all this information. And the platform can respond quickly, and it can notify users by email. And we have event replay functions in which you can see the procedure of the events. Hope users to know more about the events. And also users can write comments to give us some feedback. Users can subscribe hijacking events for their S number, and then they will get the alarming email here. Also, this page is for the hijacking event statistics. You can check by economy S number and all the yearly, monthly, all this information you can check. Also, we compare our platform with some other platforms. This is the example that our platform just responds the hijacking events, which is compliant with the raw information. But other platforms, they make run the hijack and victim. This is some compare with other platforms. Our platform, in summary, our platform has short delay, and it can support event replay and event statistical analysis and event level evaluation. And we have a benign noise report and email alarm, and we think the accuracy is relatively high. Then I will introduce some tools for network operators to monitor their IS information and their routing paths of this information. Here is a dashboard. You can just check the IS information, and this can search by IS number or organization. This is the some summary information, and here listed all the prefix of the IS, and you can search and check if they are correct. And also here are some key neighbors of your IS you can search, and you can see the line. Some lines are thick and some lines are thin. And the thick line means there are many prefix exchange between you and this peer, this neighbor, which means that this neighbor is key, is important to you. You send more traffic and receive more traffic from this neighbor. And also, this table lists all the detailed information of all your neighbors. Also, the platform, you can search from your S number to a destination. For a prefix, there may be some sub-prefix of it. So here we give all the paths of the prefix you entered and the sub-prefix of it, and we aggregate the prefix with the same path, so the operators can have an overview of their routing paths. So also you can check the routing path to your prefix or to any prefix. When you change some policy, you can check the routing path here. And also you can search, you can click any node, and it's interactive. Also, you can check by routing path. You can put 2 prefixes here and get the forwarding routing path and the reverse routing path. Here we can see they are not the same. Also, you can monitor path change, such as when you do some policy changing, do some configuration, maybe you want to monitor if the routing path changed from one to another. And all this information is convenient for network operators. Also, you can search the routing information and find the router jitter from which prefix, from which neighbor, all this information. And you can get use the Open API to get events and some detail of the hijacking events. For future work plan, we will develop an integrated Looking Glass platform and then use all these Looking Glass vantage point to check routing hijacking at the data plane to improve the accuracy. And then we will implement path hijacking detection and routing leak detection. And also we will continue community development and engagement and international collaboration. Now is the second phase of the project funded by IPNIC Foundation. And we welcome new partners to join to use this platform and give us some suggestions and comments. This is a Looking Glass vantage point. We have found over 2,000 Looking Glass vantage point. And this is an integrated Looking Glass platform and open API you can use and try. And by all this Looking Glass platform, we will do data plane detection and to. That's all for the presentation. Thanks for your attention, and comments and suggestions are welcome, and you can contact us at this email. Thank you.
Any questions? If you haven't been to the website for BGP Watch, go and have a look and throw in some of your own prefixes. It's worth having a look at. Thank you very much. All right, next speaker, Aris, where are you hiding? All right. Aris is going to talk about RPKI filtering in the data plane in IXs. Have fun.
Okay, thank you, Dave, for the introductions. Okay, let me check with the. Okay, let's start. My name is Aris. So I'm from Singapore Institute of Technology. Today I will talk about one of my collaboration work with University of Malaya, Malaysia, and then also from National Cheng Kung University or NCKU in Taiwan. Okay, the topic is very similar with the previous what they say talks. Try to secure the internet or BGP, but in here I will focus on the how we secure the routing using the RPKI by doing the ROV enforcement in the data plane, especially in the IXP. Okay, let's move on. Okay, I don't think I need to introduce the RPKI. I think everybody here is already knows about it, but I just want give some very quick example and go through about how or why the RPKI we require RPKI to secure our internet. So I will give you one example of the very famous BGP hijacking, which is YouTube. Okay, I think it's already explained by previous speaker a few days ago that one of the ISP in Pakistan actually want to block the YouTube do some sensitive content, but instead of blocking the prefix of the YouTube, but actually is try to advertise the same as a YouTube prefix, and then causing the traffic is redirected to the ISP, and then cause a massive interruption for the YouTube services. Okay, so now we have solutions, which is the RPKI. So everybody knows that how the RPKI is has been deployed. Basically, we want some way to do the validations, and here we have some cryptographically way to validate our resources. Okay, like IPv4, IPv6, and S number, and then using that what they say the object, right? We can do the what we call validation of the routing, and then finally we want to prevent the BGP hijacking. Okay, of course, in the what they say in the current deployment, we have all the RIRs like implementing the RPKI, what they say, task ensure, and then all of them will try to synchronize each other, and of course for each the enterprise or any provider want to have cache, right, or validators to speed up the what they say the validation process. Okay, so I think it will be straightforward, but and then as also mentioned by previous speaker that even though RPKI is already doing a great job, but it still has some limitations. So I just took some of the what they say limitations from Manners, if you know about it. So they have already, what they say, published some blog or report about what could be wrong in the RPKI deployment. Okay, we should know that the RPKI actually likes distributed data. Okay, so so all the what they say repository will try to synchronize each other, and of course we may expect that some of the data may not be synchronized successfully or perfectly. Okay, and then the next limitation is no guarantee that the data will be updated, because some people may not change the what they say the ROA informations if there is a changes in the prefix announcement. That it can be lead into the limitations of number 3, which is basically some of the ROA actually not match with the route that being advertised into the internet. Yeah. So and most of them is because of misconfigurations of the system administrator. And then another limitation is the maximum length. So some people say, okay, instead of creating very small ROA, and then it's very difficult, and then just put the long, what they say, length of the ROA, and then the problem is it may vulnerable to the forced origin subprefix hijack. Okay, and then the last one, I think it's very common. Nobody will delete if you are not using any prefix for your what they say network. Okay, so these are some of the limitations of the RPKI itself. But in terms of the deployment, I just quickly to some example. Since we allow, RPKI allowing us to deploy validators or kits in every enterprises or every network. So we will have some kind of excessive deployment of the RPKI kits, right? So and then we can see most of the what they say traffic is containing or replicating the data between the what they say the task anchor and also the kit itself. Okay, and then the second limitations, I think, imagine if we deploy the RPK validators in the IXP, and we only allow some of the members, router of the members that connected to the other members to deploy the what they say RPKI route validations. It looks good, but and then the problem is the data from the ROA itself, it may contradict with the other informations that provide by the IXP as a services. Okay. So this is just some explanations. So basically, do some of the what they say excessive deployment of the RPK kits, it may have some synchronization issue or replication issue. And then the second, if we deploy the RPK repository in the IXP that used by all the members routers, but if we not consolidate with other IXP service, for example like the IRR database or any other data, so it may not be consistent. And then the other problem, even though the data is valid, everything is taking the data from the IXP, but it may not be enforced. I mean, this will be some members that actually not dropping the invalid, okay, but some other member did very well. Okay, so this is some of the deployment limitations of the current RPKI deployment. Yeah. Okay, now let's move on to the RPKI informant at IXP. Okay, but the first question actually, why IXPs, right? I think everybody knows that if you want to get connected to many others, what they say, network in the world, the place that you can do is from the IXP, and then you can become part of the internet. And then usually, if you want to connect to IXP in the previous way that you need to connect physically, right? You need to bring your own cables or through the L2 connections and then plug into the IXP fabric. But now with what they say, all the technology, IP, MPLS, VXLAN, or any other method, you can actually connect to the XP from what they say, your own locations. So it makes the fabric itself can be distributed along the different locations, and then give you flexibility and also improve some resiliency. Okay, and then in the XP, actually, it's very critical when we are doing the route filtering, especially if you are doing what they say, the L3 XP. So if you are doing well for the filtering or routing policy, so I mean the EXP will operate very well. But imagine if you are doing some mistakes and then causing some root leak in the XP with like root server or whatever it is, and then you will leak all the what they say the prefix that having some problem to your all your members. Yeah. Okay. And then the idea of enforcing the what they say the validation in IXP, basically we need to understand that XP need to have a two different plane, right? I think it's already explained by a previous speaker that we need to have some kind of control plane in the IXP itself, okay, and as well as we need to have some data plane, or we call it like IXP fabric, right? So and then by separating these two, actually we should be able to have some mechanism to analyze the overall situation from the control plane before we actually deploy any policy into the data plane itself. Yeah. Okay, and then the next one actually we need to have some consolidation of the informations. Okay. Either I mean one of them it will be the RPKA cage or validator to improve the verification time, right? Because imagine if all the member routers need to go to the IRR to get some verification, it will be very difficult. Okay, and then the last one I think is most important. Actually, you need to have some consistent enforcement in the IXP. Means that if your member want to what they say block some invalid routes, okay, so every other member should do the same, right? So because if we do from the routing policy perspective for each member router, some member as I mentioned before, some member may block, but some other member may not block, and then it may cause what they say like another problem, right? Because the route will go from this member but will not go from the other members. Yeah. So this is the overall idea how we can enforce the ROV in the IXP. Okay. So the options, basically we have several options. I think there are many different what they say article or any document that you can follow. I just take like 3 of them. Okay, but basically you can enforce by the routing data. Means that what they say your enforce the what they say the control plane to only process or only what they say work on the data that actually is accurate, right, or valid. Okay, so you can combine with different data from the what they say RPKI itself, and then what they say RR data, and then appearing DB, and so on, to make your own consolidated data that that it can use that you can use to do the what they say the to fit into your IXP server or any others mechanism. Okay, and then of course the second one I think is very common, that you enforce the validation using the routing policy, right? So usually the IXP manager or route server will what they say receive some routes from the members, and then based on the what they say the policy that we deploy, and then we do some kind of what they say creating some unconflicting policy routing, right? And then the last one, I think the one that we want to discuss today, actually, like we want to do the enforcement in the level of the data plane, which is the forwarding level. Okay, so basically you can have the mechanism that how you pass the the policy from the control plane. It can be EXP managers or with some additional like SDN controller to install or to decide what do you want to do to with the packets, okay, whether you want to reject in the hardware level, okay. So this is some option that we can use, but today we just go directly that we can use the I mean, with the help the technology like SDNs. So in here we leverage concept of SDX, software defined internet exchange, and then we call it the XDA fabric. Basically, it's same as IXP fabric, but somehow it's programmable and can be controlled by the SN controller. And then we have a BSP speaker, actually similar to the route server that can communicate with the SDN controller. And then the ROV process actually is part of the application in the SDN controller itself. Okay, and then of course the process of the ROV can use a different source of the data, but in here we use the RPKI validator data. Okay, so I think the overall topology something like this. We have the fabrics, we have all the router of the members, and then we have the BSP speaker here, and then this is the SDN controller. We talk to the RPKI validator. Okay. Now this just to show some of the components. So switch we use the OVS, SDN controller we use the ONOS, and then the router we use the Quagga, and then we make some application. It's called SDN IP, and then for the validator you use the Routinator. Okay. Okay. This is some logic. So the logic I think is very straightforward. When I receive the routes, I will receive the prefix, and then I will the controller will consult to the validator using the API calls, and then okay, some result whether it's valid or not valid, and then we decide some actions, and then we decide how what kind of rule need to be pushed into the ISP fabric. Okay, so this is the topology testing that we did. Actually, we tried to create the simple topology that happened during the YouTube hijacking, but little bit we little bit modified it. Okay, so basically in here you can see we simulate one ISP try to hijack the traffic of the YouTubes. Okay, and then we found here in the BGP speaker or the route server, actually we receive two different routes here. Okay, so one of them is like hijack traffic, sorry, hijack prefix. Okay, so and then even though it's received by the BGP speaker, and then it's also distributed to some of the the members here. Okay, you can see here the members still have the prefix that hijack. Okay, but and then the controller knows that okay, now one prefix actually is a result of the hijacking. Okay, so after the analyzing or consulting with the the RPKI validator, say that okay, this is not valid because it has invalid S number, right? It will be come from here, but actually it's coming from here. And then the SDN controller will decide, okay, now I will not install any rules in the hardwares that allows the traffic from the client to go to this path. Okay, so if you can see here for the ping from the client network to the YouTube still going on. Okay, so it's not it's not affected with the hijacking that happening here. Okay, so you want to see the details? I mean, we have some published paper here. So if you have any questions, just come to us and then check with us. Okay. Okay. Now we know that we need to have some kind of more bigger scale of the testing and verifications. So as you may know, we have some test bed that previously supported by ESIF Asia to build, you can say, like BGP and SDN test bed around Asia countries. And then also thanks to the ESIF Asia, we got some awards for this works. And then we will try to use this test bed for our our works. Okay, so basically it's the overview is something like this. So we have a test bed in different locations. Singapore is just for the transit, and then especially we have the locations in Mairan, Malaysia, and Tuaran, and also some other locations. But in here we use this kind of topology to test our IXP fabrics. So we just make some overlay connections using the VXLAN, and then the configurations I think is more detailed. So I think everybody's like, no, it's just creating the VXLAN, and then you attach some of the virtual router here, connect to the one interface to the switch, and then yeah, I mean it's typical IXP connectivity. So nothing special here. As long as you have some connections between your router, and then you're able to connect to the root server, I think it will be enough. Yeah. And then this is some a view from our controller how actually is being done. And then you can see here we have the switch in the Malaysia, and we have the switch in Taiwan, and there is another switch in in other locations. And then we connect the router, Quagga-based router, to the switch, and then all the router can able to make appear with the PCB speaker. Yeah. Okay, so that's it. Thank you for your attentions. If you have any questions, just contact me, or you can access to our website, our project website in that link. Okay, thank you.
Thank you, Aris. Do we have any questions? 3, 2, 1. All done, all silent. Thank you, Aris. Now, a couple of announcements. Tonight's social is actually off-site, so you'll need a BTS card and an MRT token. You can collect those from the registration desk. So if you are going to attend the social tonight, that is where you get that from. There is still ice cream out there. Please eat the ice cream, otherwise ice cream will go homeless, and nobody wants homeless ice cream. All right, enjoy the rest of your day, and thank you for attending Innovation 2.